Hi, I'm Anay Mehrotra. I will be talking about a paper on selection in the presence of intersectional implicit bias. This is joint work with Bary Pradelski at CNRS and my advisor Nisheeth Vishnoi at Yale University. Decision makers have to make selection decisions in any context where the number of applicants is more than the number of opportunities available. Hiring is a canonical example of this. In hiring, human decision makers select a subset of applicants to give job to. In fact, selection decisions arise at every stage of the hiring pipeline, from shortlisting till the final interview. Hiring is especially relevant because it involves high-stake decisions that affect economic opportunities available to the applicants. High-stake decisions also arise in university admissions and in deciding who gets a promotion at a company. In any of these contexts, the main job of the decision maker is to estimate a latent utility, WI, of each applicant I. In hiring, the latent utility captures the value that the applicant will bring to the firm. In university admissions, it would capture some notion of the student success in the program. Suppose there are n positions in total, then the goal of the decision maker is to select n applicants with the highest sum of latent utility. They can do so by simply selecting the n applicants with the highest latent utilities. For instance, in this example, there are 4 positions, and the applicants in the best subset have latent utilities 20, 20, 18, and 10 respectively. However, all of this relies on the assumption that the decision maker can accurately observe the latent utilities. In reality, the latent utilities observed by the decision maker can be skewed due to their implicit bias. Implicit bias is an unconscious attribution of qualities or lack of qualities to members of certain social groups based on race, gender, or ethnicity. Decision makers are not consciously aware of their implicit bias. Hence, even a decision maker who is genuinely trying to select the best applicants can underestimate the latent utilities of applicants in certain affected groups. The adverse effects of such implicit bias are well documented in a variety of contexts, from hiring to promotion to education to peer reviews. For instance, in 1997, Veneras and Wold examined the peer review of fellowship application at the Swedish Medical Research Council. They found that among applicants who displayed similar research quality, peer reviewers assigned consistently lower competence scores to women applicants compared to men applicants. Significant research also documents that applicants that are at the intersection of multiple affected groups face a higher implicit bias. And many of these works stress that it is necessary to account for the intersectional nature of bias when designing interventions. Even Veneras and Wold found evidence of intersectional bias. They found that among applicants with similar research quality, women who were unaffiliated with the evaluation committee received much lower scores than women who were affiliated with the committee and men who were unaffiliated with the committee. Thus, neither gender nor affiliation with the committee explain the bias experienced by the candidates. We consider a model of implicit bias introduced by Kleinberg and Raghavan and later extended by other works. Here, there are multiple affected groups that can possibly overlap with each other, and for each group, there's a bias parameter. So for groups G1, G2, and G3, there are bias parameters beta 1, beta 2, and beta 3. The observed utility of applicants in affected groups is smaller than their latent utilities. Consider 2 overlapping groups. The observed utility of applicants in just the first group is beta 1 times smaller than their latent utility. The observed utility of applicants who are in just the second group is beta 2 times smaller than their latent utility. And applicants who are at the intersection of both groups face a higher bias. Their observed utilities are beta 1 times beta 2 times smaller than their latent utility. For more than 2 groups, the bias experienced by an applicant is the product of bias parameters of all the groups they belong to. Such implicit biases adversely affect the applicants in affected groups because, say, if you are in an affected group, then your observed utility is smaller than your latent utility. And because of this, even if you had a high latent utility, you may not be higher. Implicit bias also reduces the latent utility of the final selection. In this example, the decision maker who selects the best set of applicants, but according to their biased view of utility, would select a subset whose latent utility is more than 10% smaller than the optimal. Here, the decision maker ends up hiring less valuable applicants than they could have. As a policymaker, the question for me is, what measures or interventions can I take to reduce such adverse effects? Many interventions have been proposed. These include policies or constraints to increase the representation of affected groups, and when possible, uh, non-constraint based interventions such as structured interviews and anonymized evaluations, which reduce the effect of implicit biases on the evaluation. Apart from mitigating adverse effects, information campaigns and anti-bias training can also be used to reduce the decision maker's implicit bias itself. We'll focus on representation constraints and examine their efficacy. Often, a representation constraint is a lower bound on the number of applicants selected from the affected groups. When there is a single affected group, this requires the decision maker to select at least L applicants from the affected group, where L is some parameter set by the policymaker. Such constraints can be used in any selection task, and for any selection task, they can be used in one or multiple phases of selection, from shortlisting applicants to hiring the final interviews. The Rooney Rule is a popular instantiation of these constraints. It was introduced in 2003 in the National Football League in the US, where African Americans are underrepresented in head coaching positions. The Rooney Rule requires each team in NFL to interview at least one African American applicant for its head coach position. In other words, it works for one affected group and it sets L equal to 1. Since 2003, the Rooney Rule has also been adopted by several major tech firms to increase diversity in their workforce. This includes Amazon, Meta, and also Microsoft. When there is more than one group, then typically constraints place lower bounds on each group separately. They require the decision maker to select at least L1 applicants from group 1, at least L2 applicants from group 2, and so on. These constraints are non-intersectional. They place lower bounds on each group separately, but do not specify the lower bounds on intersections of these groups. However, applicants in the intersections face a higher implicit bias. So as a policymaker, I need to know whether non-intersectional constraints are sufficient to mitigate the adverse effects of implicit bias, or do we need to use intersectional lower bound constraints? For instance, with two groups, intersectional lower bound constraints will require the selection to have at least L1 applicants who are in just group 1, at least L2 applicants who are in just group 2, and at least L3 applicants who are in both groups 1 and 2. Before comparing intersectional and non-intersectional constraints, let's go over some of the main prior works. These consider a single affected group and assume that the latent utilities of applicants are drawn from the same distribution. The latter captures the belief that the set of applicants in each group have the same distribution of true or latent utilities. Under this setting, Kleinberg and Raghavan give conditions under which the Rooney Rule improves the expected latent utility of the selection. A policymaker can look at these conditions and decide whether it's beneficial to enforce the Rooney Rule. Solis et al. Consider lower bound constraints beyond the Rooney Rule. They showed that there is a lower bound constraint such that the decision maker required to satisfy this constraint selects a subset with near optimal latent utility. In particular, this subset's latent utility approaches the optimal as the number of applicants increase. This means that irrespective of the decision maker's implicit bias, enforcing these constraints ensures that they achieve a latent utility close to that of a completely unbiased decision maker. However, both of these results assume that there is only one affected group and all applicants in this affected group face the same implicit bias. Neither of these assumptions is true with intersectional groups. We consider multiple overlapping affected groups, and in our first result, we show that when latent utilities are drawn IID, then no matter which non-intersectional constraints are used, if a decision maker is biased, then they lose a constant fraction of the optimal latent utility. The fraction of the latent utility lost does not depend on the number of applicants, and it increases with the amount of implicit bias. When a decision maker has extreme implicit biases and the utilities are drawn from the uniform distribution, then the fraction of utility loss can be as much as 10%. This result shows that non-intersectional constraints are not sufficient to mitigate intersectional implicit biases. And this is in contrast to the case with a single affected group where, given a large enough applicant pool, non-intersectional constraints could ensure that the decision maker had near optimal utility. Our next result complements this and shows that intersectional constraints can mitigate implicit bias. So there are intersectional constraints such that irrespective of the decision maker's bias, if the decision maker is required to satisfy these constraints, then they achieve near optimal latent utility. These intersectional constraints are also natural. They require the decision maker to select at least a near proportional number of applicants from each intersection. The constraints themselves do not depend on the bias parameters or the distribution of latent utility. This is useful for policymakers because as a policymaker, I can use these constraints even when I have no idea about the distribution of utility or the specific bias parameters. And I also don't have to worry about changing my policy if the bias parameters or the distribution of utilities change in the future. In combination, both of our results show an advantage of intersectional constraints. And in the paper, we also show that these results are robust to deviations from this particular model of implicit bias to ones where the bias at the intersection of two groups is different from the compounded effect of bias of each group, and where the bias does not act through multiplication with bias parameters, but rather through some arbitrary increasing function for each group. I'll explain the main ideas of the proof with two groups that divide the set of applicants into four intersections of equal size. Our first observation is that the subset that maximizes the latent utility selects a proportional number of applicants from each intersection. Complementing this, any subset that overrepresents one or more intersections has suboptimal latent utility. Notably, both of these results hold because utilities are drawn IID, and because of this, each intersection has a roughly proportional number of applicants from the top n applicants. The main lemma that we prove is that if a decision maker has implicit bias, then no matter which non-intersectional constraints are used, the decision maker's output will always overrepresent at least one intersection. To gain some intuition about this result, suppose that the latent utility of all applicants is exactly 1. Suppose that the decision maker now selects a subset that does not significantly overrepresent any one intersection. We can alter this subset by adding one applicant from I0, who's in neither group, and one applicant from I12, who's in both groups, and remove one applicant from each of I1 and I2. The resulting subset also satisfies the non-intersectional constraints because we removed one applicant from G1 and one applicant from G2, but we added one applicant from both G1 and G2. The new subset's utility is additively 1 minus beta times 1 minus beta 2 higher than the original subset's utility. And this is a positive quantity whenever the decision maker is implicitly biased. We can repeat the same swapping argument multiple times to get a new subset which satisfies the constraint, which has a higher observed utility than the original subset, but which significantly overrepresents the two intersections. This contradicts our initial assumption that the decision maker selects a subset that does not significantly overrepresent any intersection. In general, this swapping argument will not work beyond this specific example. But for distributions, such as the uniform distribution, we can show that the swapping argument works a sufficient number of times, and this proves the result for the uniform distribution. The downside of this proof strategy is that it's not straightforward to extend to other distributions. But as a policymaker, I may have some idea of the distribution of utilities, and I would like to know if non-intersectional constraints would lose latent utility for this specific distribution. To answer this, we give an optimization program parameterized by the distribution of utility, such that for any distribution and non-intersectional constraints, its solution is close to the subset selected by the decision maker. We show that the objective of this program is strongly concave, Lipschitz and Lipschitz continuous in certain parameters, where the specific strong concavity and Lipschitz constants depend on the specific distribution of utilities. We then use these properties to identify a family of distributions where non-intersectional constraints always lose a fraction of the optimal latent utility. To conclude, intersectional implicit bias has a negative effect on the quality of the output subsets. When the latent utilities of applicants are distributed IID, then any non-intersectional constraints lose a constant fraction of the optimal latent utility. In contrast, intersectional constraints can achieve near optimal latent utility. Our results highlight the advantage of intersectional constraints and give another reason to use intersectional constraints over non-intersectional constraints. There are several directions to extend our results. In practice, any estimates of latent utilities will have some amount of noise, and we don't currently consider this noise in our results. It's also important to study the long-term effects of intersectional versus non-intersectional constraints. For instance, how do different constraints affect the behavior of applicants in different groups? And what effect, if any, do the constraints have on the implicit bias of the decision maker? With that, I'd like to thank you for your attention, and I'll be happy to answer your questions in the Q&A session.